Hey everyone, welcome to our webinar on microgrids automation. Thank you all so much for joining us, and we're so excited to share with you some ideas on the new challenges about the modern networks. I'm Charlie GERS. I work for the marketing department here at GERS. If you have any questions, just please submit them and we will read them at the end of the presentation. For starting this presentation, I will give a brief introduction of our company, GERS. GERS is an electrical engineering consulting group that was established in 1981. To date, we have completed over 6,500 engineering projects and over 3,700 electrical studies in over 45 countries. On this slide, you can see the countries where, let me see. Is Leineker? Leineker's
yes.
on? Okay, so yeah, well, put the slide where the countries where we have carried out the projects from our offices.
Okay.
So you guys can see, this is the countries where we have carried out our projects from our offices, which once again has been over 6,500 projects and over 3,700 electrical studies in over 45 countries. For this presentation, we will be accompanied by two special guests, Dr. Juan Manuel GERS and Master Leineker Palacios. Dr. GERS established his electrical engineering consulting company in 1981, which today has offices in the US, Colombia, Mexico, and Chile. He has a long-standing career in electrical engineering, having worked in academia as a professor at Gonzaga, Penn State, and Universidad del Valle, in the public sector as a Vice Minister of Mines and Energy of Colombia in 2002, and in the private sector with the GERS companies. Master Palacios has made some publications about smart grids, and he has led research developments in smart grids, coupled with more than 8 years of experience in electrical network simulations and real-time integrations. Today, our presenters will be explaining us the different topics, challenges, and real applications using our GERS laboratory. In this slide, we are showing the content for this presentation. Welcome and enjoy the webinar.
Thank you very much for the presentation. I would just like to mention, going back a little bit to the previous slide, that we have here basically 6 topics. We'll be presenting, after the introduction, the fundamentals of microgrids, concepts of hosting capacity, the architecture, the simulation methods, and at the end, we would like to present a lab that we've implemented to simulate and work with microgrids. We will have at the end the chance to present some conclusions and, of course, to answer questions that you guys might have. Again, thank you very much for joining this webinar, and welcome to this. We really hope that it will offer you some good ideas about this fascinating field of distribution systems. Okay, first of all, I would like to say that microgrids is a rather new concept that has been around perhaps from the beginning of this century. Years ago, beforehand, perhaps at the end of last century, we would talk mainly about distribution automation, and then the whole concept expanded and it became rather called like smart grids as a whole. And part of the smart grids, of course, is the microgrids. In this case, of course, as we will see later, we will be talking about small systems that are comprehensive. I mean, they would have generation. We couldn't talk about transmission, but yes, of course, distribution systems. And one of the features that, of course, we know that microgrids have is the possibility of generation mainly with renewables. I would like to emphasize the word mainly because it doesn't mean that necessarily all the sources come from renewables. They could be also from fossil, like diesel generators. We'll see that. Anyways, in this first picture here, we just show a very typical PV facility, photovoltaic facility. I would say that normally microgrids do not have the solar thermal type of generation, mainly PV. And well, here you will see the possibility of looking at the different strings, and of course the control model of the PV facility. We will not be talking in detail, of course, about the features of the system. But of course, we should have here the actual cells, the inverter, the AC filter, and the connection to the network, as you can see here, with the corresponding control. I mean, the maximum power point tracking to make sure that we get at its best the solar light, and of course the pulse width modulation, which is perhaps the core because it is basically the control of the inverter. Anyhow, this is a typical facility that we wanted to bring here to start our presentation. It is interesting to see more or less at the bottom right, you see the number of units that we have. In total here, we have, as you can see there, 2 loops, and each one would have 10 transformers. Each transformer would have 2 inverters, and actually inverters would have 5 arrays. The whole thing is at the left of this slide, and it's beautiful. Actually, I had the possibility to visit it. It was in 2017. This facility happens to be at the southeast of Puerto Rico, which unfortunately the same year we conducted the study, the whole island was hit by the Maria hurricane, if you remember. But anyhow, it is a good starting point to show a typical PV facility of a medium size, because we are talking here about more or less 23, 24 megawatts. Okay, what we should start talking about is what is the definition of microgrids. We all might have different definitions. Actually, if you talk to 10 different utilities, I'm sure that you will get 10 different definitions, but we prefer perhaps to refer to those at least used very much in the US. One of them is given by the Department of Energy, the DOE, stating, I will just read here, a microgrid is a group of interconnected loads and distributed energy resources within some boundaries, and a microgrid can connect and disconnect from the grid to enable it to operate in both grid or islanded mode. Basically, this is summary. This is the definition given by the DOE. The link is underneath, and of course, you will get the lecture and you can go to that website. The other definition is by SIGRE. This is an European institution that states that microgrids are electricity distribution systems containing loads and distributed energy resources that can be operated in a controlled, coordinated way, either, let's say, while connected to the main power or while islanded. So, yes, I think that both definitions, of course, agree in different words. They mean that we have electrical distribution systems that can generate their own energy and that, of course, are controllable either remotely or locally. And this definition is quite simple but quite clear. You can see here that also, especially in the SIGRE definition, we talk about different type of generators. One of them is the storage devices that are gaining a lot of momentum these days because, of course, they can supply power, especially at night when PV facilities, of course, are off. So in summary, we would say that microgrids are part of electrical systems that are self-supported, that can work either connected to the main supply or to the network, to the national grid, whatever, or isolated. Some more clear, I would say, presentation of these topics could be given in this very simple slide, where you can see at the left of this slide a typical system where the source comes from the national grid, let's say, and goes to a suburb of a city and feeds different users. Now, if we see here the system to the right, you will see here that new components appear. And in this case, we can see, of course, the PV facilities. In this case, we have two, and we have only one wind facility, one generating facility. Both the solar facility, the PV facility, and the wind generation facility are, of course, renewable sources. That's very interesting. However, as I said, not necessarily all the generating sources in microgrids come from renewables. Anyhow, the beauty here is that we can see again to the right in this yellow circle that the system can grow, and eventually the system can impact a lot the main distribution system of the corresponding utility. And that's why, if like in this case, we have two main sources, one is run by, let's say, solar facilities, the other by a wind facility. If they become rather large, it's better for them to make up what we call a microgrid in that distribution system. So each one really can handle its power, can handle its load without affecting the main distribution system if one of them goes out of service or gets disconnected. That's when we have to operate properly our microgrid. The point is that if we have a microgrid and we don't have good care about the operation of it, then there are several situations, and that's why we always raise this question: what if, we lose the main power? What if we lose the actual generation? In fact, if we rely on solar facilities, we will, of course, lose the power at night. In a wind facility, we will lose the generation when there is no wind, of course. So there are many questions that arise, from the existence of this type of systems. And those are the ones that we have to approach properly. Okay, I will present here three very basic cases. And this will give, of course, much clearer reference or understanding to what a microgrid means. Mind here that we have a load of 60 kilowatts. We have a generation. We will see here that the generation can go up to, say, 9 kilowatts. And of course, we have the primary network or the national grid. You can say, or you can wonder, why so small loads? Actually, we are talking about houses, basically, even small houses. 60 kilowatts could be even too small, but still, this illustrates very, very well the concept of microgrids. And the first case that we will see here on this very simple situation where we have this load of 6 kilowatts, the PV generation facility and the connection to the distribution utility, is that we generate, say, in the PV facility 9 kilowatts, which of course is larger than the generation of the load. So if we have this situation, we can, of course, imagine that there will be some surplus, of course, 3 kilowatt surplus. And then in that case, our load takes, of course, 6 kilowatts. The PV generates 9 kilowatts. And this is the typical case, according to the IEEE 1547/2018, that we have a continuous operation, where basically our PV facility feeds the load associated and the surplus is sent to the distribution system. Easy. Now, the second case is where we generate not 9, but 6 kilowatts, which is exactly the same amount that the load demands. So in this case, we can see here that we could, in theory, perhaps be disconnected from the primary network, of course, because the generation is just enough for the load. Both are equal to 6 kilowatts. However, a good question arises here. And the question is if we can open, as simple as that, the connection between the two, between the primary network and the what we call now the microgrid. And the point is that, I mean, if it depends only on demand, yes, we can of course open. I mean, the generation is good enough, but are we sure that the frequency control given by the PV is enough to keep the voltage or the frequency, say at 60 hertz, if it is in the Americas continent, or 50 hertz if it is in Europe or Middle East? Now, the question depends basically on the actual PV, on the inverter of the PV, because we have to make sure that it can control also the frequency. The case might be that the inverter doesn't have the capacity to control frequency, and in this case, we cannot open isolated from the system. If the inverter has that ability, or if in that microgrid we have a generator that can sustain the frequency at 60 hertz, if that is in the States, for example, yes, then we can disconnect our microgrids from the system, because the generation is good enough to supply the load, and the inverter is capable to keep the voltage, the frequency of that system at 60 hertz. Now, that is, of course, if you go again to the same source, the IEEE 1547, we can say in that case that if we take the definitions, we know where the point of common coupling is. And in this case, we can have either the intentional island or the unintentional island. But still, we have to make sure again that the system, in this case, the inverter, is capable to keep the frequency. Of course, that if the case were that we generate 6 kilowatts and we have 6 kilowatts in the load, then we wouldn't have any demand from the primary network. Okay, the last case, just to illustrate the fundamentals of microgrids, is when the PV facility is capable to generate only 3 kilowatts. Let's suppose that that is at the end of the afternoon when we are having the sun sunset. In that case, of course, we should import, if you will, power from the network, which is indicated here. Of course, the math is quite simple. If the load takes 6 kilowatts and I generate only 3, I would need from the network 3 kilowatts to make up the 6 kilowatts easy. What I want to emphasize here is that according to the IEEE 1547, the microgrid becomes a load. So with that, I think that we can complete the, let's say, fundamentals of what microgrids mean. I would like to refer again to this standard IEEE 1547. The last issue was or is from 2018. Is the IEEE standard for interconnection and interoperability of distributed energy resources with associated electric power system interfaces. And I recommend you, please, to refer to this document, which I think is the best in the world regarding the operation in general of distributed energy resources. The 3 cases I just mentioned are indicated here when we generate 9 or 6 or 3 kilowatts. And in all of them, we have the microgrid concept. Characteristics, I think that I already mentioned those, are self-supported. So, I mean, they are good enough to supply their own demand. They have the generation enough to meet the load. Microgrids are of different sizes. I mean, we can say that we have microgrids of 500 kilowatts, 1 megawatt, 10 megawatts, etc. Normally, as I said, they are fed from renewable sources, but not only. Again, we can have fuel generating plants, especially diesel if we are talking about the small sizes. And also microgrids, can work either isolated or connected to the network. There is a type, of course, of microgrids, and that is the microgrid that exists in very isolated places where it is not possible to rely on the national grid connection, for example. In that case, it is of course mandatory to run the microgrid in the isolated way. The benefits are many of microgrids. Number one, they are a portion of a system that can run almost autonomously with very good standards of efficiency, uh, and the operating costs are very low. And these benefits really indicating the importance. Uh, I would say, in my opinion, the network restoration. I mean, the possibility to implement FLISR is remarkable. Fault isolation and system restoration is great in microgrids. So the reliability indices like SAIDI, SAFE are very, very good. And the possibility to recover, I mean, the resilience of microgrids is outstanding. Of course, the optimization of generation, especially these days when we look for the renewables to have an important role when it comes to generation. We can see what is happening in Germany, that nuclear facilities are being knocked down, whereby microgrids or in general distributed generation, especially made up by renewables, are playing or are going to play a very important role. The easiness to synchronize the generation with the networks, the possibility to implement demand response. So definitely, microgrids are taking very important place in the distribution systems. Finally, here, when I say finally, I will just illustrate um, in a very simple way how we will consider the case of microgrids. You will see here a nice representation where we have three main transformers. We have different types of loads. Actually, this is the rather comprehensive system where we do not have any renewables. So in this case, with the help of this software that we call NIPLAN, we will start making a very simple illustration. First of all, let's consider the network without any additional generation source other than the connection to the network. So if we run the case here, we can see that we are importing from the network system. I hope that you can see my screen here, 15.42 megawatts. And we are sending to the microgrid again 5.42 megavar. So 15.42 megawatts, 5.42 megabars to the system. And we can see here, perhaps briefly, or I hope that you can see here that the voltage levels in all cases are very, very good. I am running this online, so that allows me to present you briefly here what the result is regarding losses. Please try to remind this figure, 0.31 megawatt. That is a magic value. Why? Because we are talking about of improving efficiency, and losses, of course, plays an important role in the operation of distribution systems. So for this very simple system, we are getting 0.31 megawatts. That means 318 kilowatts of losses. Okay, now we are going to consider 4 different sources of generation made up mainly by renewable. So you can see here the same system exactly as I just presented that, but it has one PV facility here to the bottom connected to node N2-4, and here we have a wind generation facility. These two here, Gen 1 and Gen 2, actually are not necessarily from renewable sources. And we presented this example on purpose just to illustrate that not all generating sources come from renewable generation. Okay, in this case, still we are connected to the network. And if we run the case, as I am doing here by pressing this button, we get here that the values again show very good voltages in all nodes. We will not go in detail, but let's see in the summary the value of the losses that show here that we brought the 0.31 megawatts. If you remember, almost to half, 0.17, and it is remarkable. I mean, how we improve the system just by installing generating facilities. Again, in these days, mainly from renewable sources. Now, if we would like to see more, well, we could go here to check, for example, the results for the node, I mean, for the voltage of the nodes. And here we will see that all the nodes, if you can see here, have voltages that fulfill the standards of plus minus 5%. All of them are in between that range. That's super. Now, finally, if we disconnect the microgrid from the system by opening the two breakers, and in this case, we have to enable one of the generators as the slack generator, then we come to this case here where we work the system as an island. When we work the system as an island, you will notice here that the two breakers are open, that the generator, well, became a slack source, because that is, we need, of course, for any system to have the slack bus bar or generator. But the system is now disconnected. If we run the same case, quickly here, we can see that, again, the voltages are within the corresponding margins, plus or minus 5%. We don't have here any, let's say, transfer from the national system. It's 0 megawatts, 0 megabars. What about the voltages? Are, again, good enough? And the losses? The losses became 0.17. If you remember, connected to the system, now the losses are, let's see, 0.18, a bit higher than when the system was connected entirely, which is, I would say, expected, of course. I mean, we are now running with the system disconnected from the main grid, but still, the losses are lower than those that happen when the system doesn't have any renewable or any other generating source. What shows this? That yes, of course, a very well planned microgrid can work perfectly. Finally, two main points before we come into what we call hosting capacity. We have here another microgrid. In this case, if we run the system, we can see that the voltage is, as the drawing shows here, is exactly 114. So we are exceeding the voltage. And why this happens? Well, because we are generating only 100 kilowatts, but the distance here is extremely too long. It's 49,000 feet. That is more or less equivalent to 15 kilometers. That's a lot. So it is not as simple as just installing the PV facility or the wind facility and connecting it to the system. No, in this case, of course, we have the inverter set like a PC, power and cost phi. So yes, we are fixing here the generation. If we run this PV facility as PV, okay, we can support the voltage at 114, but we would require a lot of kilovar being injected from that source that we not necessarily could have. Now, likewise, for example, if we increase now the number of cells, let's say here we have only one cell. You can imagine if we go to 5 cells, if we are happy with the system and want to go to 5 cells, that will bring the whole voltage to a value of 158, which is, of course, a bit too much. So the point here is that when we connect photovoltaic facilities, wind facilities, other type of generation sources, we have to be very careful about the network or about the system where we are going to connect that. That will lead us then into what we call the hosting capacity. I mean, how our system in this microgrid can accept generating sources either from photovoltaic, wind, or other types without violating the values. So this part is going to be presented by my colleague. Here, just a quick summary. In this case, you could see here that if we go to, let's say, 15 kilometers, that means 49,000 feet, then our voltage at the node N12, which happens to be this one here, N12, can go to 114 with one cell. But if we have 5 cells, we go up to 1.57 easily. That's why actually even this figure here doesn't show that the scale. Of course, that jumps out to a very high value. So the location of the let's say generating facilities is essential in order to determine whether or not the system can host the new generation. Okay, the concept of hosting capacity and the demonstration of how our lab works is given by my colleague here, Leineker Palacio. So Leineker, please, you take control of the presentation. Actually, since I presented those slides, you can jump them out.
Okay. Thank you very much. Good afternoon, Dr. GERS. Good afternoon, Charlie. Good afternoon to all attendees. This is my pleasure to share this webinar with Dr. GERS. And in this case, what I'm going to do is to continue presenting here some capabilities that we need for doing some analysis about hosting capacity. That we can see here is that in the case that Dr. GERS presented before, it was a case where basically we are having an extension of the length line, and that we can see here is for doing the analysis on the more complex network, we have different scenarios that they can occur on the network. The first topic is, for example, speaking about the penetration and speaking about the location of the distributed generators. In this case, for example, we are speaking the first scenario where we are having a first location for having a penetration of 2%. And if we are trying to reach the same penetration level, we will be speaking about, for example, a different location for having the same added power. And the same case, we will be increasing the scenarios. They will be different scenarios for having the same penetration of the voltage levels and, of course, the power capability on the distributed generators. Now, if we consider the first scenario, we can extend here, for example, for the same location, but we will be speaking about new penetration or 4%. We are having here this illustration where we will keep the location of the distributed generator, and we will increase new locations for having a new penetration, and that will be the same cases for the integration of the distributed generators. Now, for having the 100%, of course, we will be having exactly the same possibilities to integrate that. But however, the main topic here is, okay, what are our nodes and the location that they can affect the operation of the network in steady state conditions. So let me show you, for example, here. This is a more complex network, and this network is for the distribution system. And in this distribution system, we can see that we are located here directly on the map server, and that we can set here is checking our hosting capacity simulation in order to detect the affectation of the distributed energy integration on the distribution system. Now, that we are doing here is running an automation of all probabilities or the system or different locations that we could have on the network. And according for the different locations, we will be specifying here, okay, that we can do is keep a matrix risk in order to detect the different scenarios that we could have on the network. For example, different penetrations that they can affect or not the limit violations that we are having here, the illustration, different positions and different scenarios, as I explained it before. That, for example, here we can see that how some scenarios don't affect the limit violations. And after that, we have a yellow zone where basically we can see that some of them can cannot have a negative impact on the network operation, and some of them will be out of the limits. And finally, we will be placed here in a red zone where basically all the scenarios will be having different limit violations. Presenting here the calculation that it was complete here using the power system analysis tool, that we can check exactly is the results directly for the different limit violations. It was presented for this case or example where some of the scenarios are having here a proper operation. Some of them will keep in proper operation, but after of the red zone, we will be keeping here that a negative impact. And most of the scenarios will have in here an impact in specific nodes. And it will keep and it will provide us different tools in order to detect the proper or not installation of our distributed energy resources. And also it can be effective for the electrical vehicles that it can be analyzed on the power system analysis tool too. Now it can be checked for the different variables that we can check, and for each one of them we will be keeping how will be our matrix risk and what will be the different scenarios that can affect negative the network operation. Well, once we did this introduction about the planning the network with penetration of the distributed energy resources, it is very convenient to speak, okay, about the microgrids, where once the installation of the distributed energy resources are placed on the distribution network, we will need to keep the operation of the system in normal conditions without limit violation. And as it was presented before, some countries have had different affectations due to the high penetration of these kind of sources, that it was very, very important to implement some architectures for controls where the microgrids have been implemented for having an objective function. And that we are showing in this slide is that the IEC standard provides an control architecture where in the top level we will be speaking about an optimal dispatch of the system and the market and logistic, what will be the main purpose or the reason because the microgrid was implemented. And here also we will be having here a primary control about our generation systems because they will be very responsible for the stability of the network. In addition to that, we are showing here some standards that they are focused on the automation scheme for the networks, and some of them are for the technologies for advanced metering infrastructure, for example. Some of them are for specification in different practice on interoperability, cybersecurity. Some of them are for different communication protocols that they can be implemented or used on the network operation. Let me show you here in an easier way that the architecture, the control architecture in microgrids is split in three main control strategies: the primary, the secondary, and the tertiary control. Primary control is seeks to the availability of the network can operate even in island mode. And it is very noticed here how we have implemented a control strategy to keep our voltage and our frequency in proper values. Secondary control seeks the availability to move our stationary point to a different condition. And finally, the tertiary control, that is the core when we speak about the optimal power flow solution. That is the reason because the microgrid was implemented. What is our objective function? Would we like to reduce the losses? Would we like to increase the environment or reduce the environment impact? Would we like to have an economical dispatch of the generators? And in this case, these controls are implemented directly as a complete set for the microgrid operation. It was implemented here using some relays, and the relays will send digital and outputs and inputs in order to control the network. Well, the another topic here is for speaking about different challenges, because we are trying to reach the main methodology to operate the microgrids. And one of the main issues that we are having for the penetration of the microgrids is the different or complex operation that we could have due to the different affectation on the operation, mainly due to the renewable sources. We are not sure about the generation of the system. We are not sure about the topology. And we are presenting here specifically 4 issues that they are commonly known on the microgrids operation, and of course, and they are issues for simulate them. There are many types of the ERs, the different changes on the demand, many topologies that we have, connection or disconnection of the elements, and the bidirectional flows that they are very, very normal, the occurrence in the microgrids operation. Well, for that reason, it has implemented different algorithms to simulate the microgrids. And that we are showing here is the IEEE 1547 has represented different operation modes of the DER that they have allowed to simulate the microgrids. It has been noticed that we have the conventional control modes on the conventional power systems, and the IEEE 1547 has specified here an additional modes that they should be able to be set on the DER. Some operation modes are for keep the voltage, some of them are for keep the reactive power. And we can see how, according to the active power that is being generated, we can have a control on the power factor, or we could have a control according to the voltage profile. The another way is the simulation of the microgrid in dynamic simulation or transient stability and in short circuit simulation. First of all, it is noted that some models are presented in the WEC where some of them can be used in dynamic simulation, especially for inverter-based resources, where some of them can be adopted on the dynamic simulations for checking the stability of the system. And the another way, we have the new standard IEC 6909, and this is the latest standard that considers the penetration of this kind of sources, where some of them in general can be considered as a current sources. It means that if we have different fault locations, the contribution of this kind of sources will be the same. This is the model that we can set in this kind of sources: normal power station, DFIG station, or the typical application in the PV system in the converter applications. Well, all these considerations have been taken into account using our real technologies that we have in our microgrid laboratory in GERS, USA. That we are presenting in this slide is that the different sources that we can implement in our microgrid, and we can see here that we have a conventional generation using the synchronous generator, and this synchronous generator can replicate the operation, maybe a diesel or the conventional system that we could have in our microgrids. We also have an inverter that is able to convert the energy from DC to the AC, and the most special case here is that we have a source, and this source is able to emulate any condition on the irradiance profile or on the storage. In this case, that we can say here is an emulation of the system that we are also able to replicate here using our real PV, and that we can do here is having a variation of the irradiance profile. Well, the operation of this can be automated using the technologies and the control system, and that we are going to show here is how could we set the primary controls, the secondary controls, and the tertiary control. We can see how the excitation can be controlled in a manual mode or having here the automation of the system. Basically, we know that if we would like to increase or reduce the voltage, we will have in here a variation of the excitation of the system where we will be increasing or reducing the reactive power. Now we have here our servo machine, and in this servo machine, we are also able to control the RPMs when the synchronous generator is disconnected to the network, or the torque when our synchronous generator is connected to the network. In island mode, we will be having here a control of the frequency where our frequency reference will be the servo machine, and connected mode, we have our servo machine by operation in torque mode. All of them was connected here, and our primary control was implemented using here some IOs, where they are controlled using a very known technology, an Arduino, that using the Arduino, we will be able to send different orders to increase or reduce the reactive and the active power. That we are having here is that the control will have in here the connection of the synchronous machine, but we can see here that finally we can connect or disconnect to the external network. We can connect or disconnect the load, and we can also consider the participation of the inverter. The technologies on the real measurements are coming here using digital technologies or IEDs. Some of them are especially for measurements, some of them are designed or they have participation also for some protection schemes. And we finally have implemented an SCADA system that is able to control remotely the microgrid. This is the single line diagram of the system, or this is a quite representation of the system that we can set here. We can see here our synchronous machine. We have here our point of common coupling, and we have here our solar generation, and finally we can modify the load. Well, some specification in the IEEE 1547 is about the synchronization, and that we are using here is connect or disconnect our synchronous machine. For connect or disconnect our synchronous machine, that we did was implement here. We are having here a real-time scope of the microgrid. What we have here is the synchronous generator. We have here our measurement devices, and that we have here is the excitation of the system. Now that you can see here is the RPMs of the generator are operating in normal mode. Now, in this moment, we have our synchronous generator connected to the network, and we can check that exactly using here our SCADA system that we implemented here for having here an operation of the synchronous on the synchronous machine connected or disconnected to the network. That we can do here is open or close the circuit breaker, but it is not easier to close the circuit breaker if the synchronous machine is operating in island mode. Why? We need first of all have a synchronization of the system, and the synchronization of the system has been implemented here in the auto synchronization, where the relays will be increasing or reducing the excitation and the RPMs to keep the frequency. This is the single line diagram that represents the system that we implemented here for having the connection or disconnection of the synchronous machine. And the synchronous machine can be operated here in both, and we have our different IEDs. They are able to send the order to open or disconnect the circuit breaker. Well, the another topic that it is specified in the IEEE 1547 is about the interoperability and the communication protocols. The IEEE shows how will be the architecture or communications that they can be used for management of the microgrids. And we can see here how our SCADA system and DER management system are here. We have here an operation using the LAN or the networks, and in this level we have physical connections, and this physical connection will be having an application directly on the primary control system. In our architecture, exactly we are trying to keep that recommendation, and in this recommendation that we have here for each one of the sources and even for the load, we have different measurement devices, and these measurement devices are sending in real time the measurements, and the measurements that we are using here is a communication protocol that finally we are able to control our Arduino that sends the control or the set points to keep the operation in normal conditions. And finally, in our SCADA system, we will be able to remain an operation of the system using our LAN connection that allows to access to our SCADA system from any place. Well, in this moment that we have here is our system, and we have here our technologies from different manufacturers in IEDs. And we can see how in our SCADA system, we have here a connection connected to our synchronous generator, and we are having a generation of the active power and the reactive power. This is the initial operation of the system, but if we would like to set a secondary control that is able to send an order or set points or to our Arduino, we are having here, for example, an initial set points for 300 watts generation of 300 watts and generation of 200 bars. And once I enable here the control, the remote control, that we can see here is that the Arduino is trying to keep these set points. Now we have here the watts, and we have here how the bars are regulated to our set points that we have defined here from our SCADA system. The main topic here is that in this microgrid, we have three sources: our synchronous machine, the external network, and the inverter that is able to replicate the conditions according to the radiance profile that we have defined. As Dr. GERS explained it before, we need to keep a reference on the frequency if we would like to keep the operation of the microgrid connected or disconnected to the network. In this case that we have here in this technology about the solar generation, this technology doesn't allow to disconnect the network. I mean, the inverter is not able to work by itself. It needs to work connected to a reference point in frequency. However, we have a synchronous machine, and the synchronous machine is able to keep the reference in power and the reference in frequency and the reference in voltage. But it is depending on the technology of the inverter. The another topic here is we are going to speak about the tertiary control, because in this case the set points that we have defined here, I can change here and I can move the set point to a 315, and we can see how the Arduino is controlling again the microgrid, that we can see here how the microgrid is being affecting to the set point. And now we have here the new set point. However, these set points in general should not be added manually. We need to implement a tertiary control that we have added here using the cloud architecture, using, in this case, the web services that are provided by Niplan. In this case, we are using the Niplan web service for the optimal power flow solution. Well, what I'm going to do here is open the microgrid, and what I have here is an initial condition of the system. This is the digital twin of the microgrid that is on the cloud, and this cloud is having here in real time the measurements coming from the generation and coming from the load. And initially I am running here a load flow, and using here the load flow, what I can do here is we can implement here the set point on the synchronous machine, and if we try to keep the set point coming from the Niplan, we can see how this initial set point is implemented, and we can see the microgrid, the control of the microgrid is according to that set point that Niplan has sent. However, that is a load flow. And in this case that we have initially defined in our microgrid is a control for having an economical dispatch of the network. Now that I'm going to do here is move to the optimal power flow, and I'm going to run the optimal power flow solution. In this case, the optimal power flow solution was for an economical dispatch, where what I did was to define highest cost coming from the external network, a medium cost in the synchronous machine, and low cost using the inverter. And Niplan is suggesting these new set points for our synchronous machine. In this is a suggestion for an economical dispatch, and it allows to implement the tertiary control of the microgrid. That means when I get again the new set points that Niplan specifies here, these new set points are coming from our operation of the system, and we can see how these new set points are implemented by our Arduino, and our Arduino will try to keep these new conditions. And we can see how our active power is increasing and how our reactive power is decreasing. And of course, this will be the balance of the power on the network system. Well, in general, the optimal power flow solution is formulated as a nonlinear function. And in this case, our objective function was for optimization of the economical dispatch. This is the architecture that we presented for the tertiary control, where our SCADA system is controlled using web services from the calculation that is able to have the results from the digital twin of the network. And finally, this send the new set points to our control. Finally, it is very convenient to show the implementation of the microgrids around the world, where we can see how in the US many implementation of microgrid for researching purposes and different affectations. And as I am copy here from this source on the Department of Energy of the US, this test comes from the Department of Energy because it shows two examples that real microgrids that they was implemented in the US. The first is in California, the another one is in Colorado, and this test is very good because it shows the importance of the or what would be the reason because any implementation of the microgrid would be used as a solution for the conventional or modern network implementation. Another microgrids around the world, in Canada, in Germany, in Italy, in Japan, Chile, Brazil, Venezuela. Well, finally, we have some conclusions that maybe Dr. GERS can present us.
Well, I will present this rather quickly in order to have some room for questions that you guys might have. But basically, we just wanted to illustrate how microgrids or microgrids could be analyzed and how they can be modeled. And so how can the many advantages like sustainability, resilience, reliability, efficiency, etc., you see, can be derived from the application of microgrids. Lineker did a wonderful presentation about the tertiary control. Actually, we have here a lab that he's managing very well. And perhaps in other opportunity, if you guys have any questions or would like to see how it works, we could greatly show that to you. But yes, the point is that even in a very simple size of microgrids, the benefits can be well illustrated. Something important is the cloud architecture, and that is something that we are working a lot, especially because we have the possibility to use NIPLAN. NIPLAN is a wonderful power system analysis tool that works with data in the cloud. I think that in summary, microgrids just came to stay here forever, I would say. We have to be able to model them, to analyze them properly, and of course, to take advantage of the many benefits. With that, I think that we can close this presentation. We know that we are actually 1 minute to 4 o'clock Eastern time, but still, if you guys have any question, I think that we could take some 2, 3, 4 minutes, to try to answer the question. So if we have, JJ, any question, please let us know.
Thank you for the informative presentation, Dr. Wongers and Lineker. And yeah, we actually do have a few questions here in the queue. So we will begin with the questions and answers portion of the webinar. The first question is, for the microgrid controller that you developed, can we use it in other systems?
Well, the initial implementation that we did was for our microgrid that according to the technologies that we have. As Dr. GERS explained it initially on the presentation, we have different microgrids, and the microgrids don't have a specific size, don't have a specific architecture, because the microgrid will have different configurations according to the location or the purpose because it was implemented. So we think that if we have maybe the same technologies or the same features that we could approach in our microgrid controller, it could be implemented. However, that the main purpose in this integration is for presentation of initially how will be the implementation and how can we check the criteria or the limits that as they was specified in the IEEE standard for the integration of the microgrid. But I think that yes, but it depends. It depends if the microgrid will have the same architecture.
Awesome. For the second question is, can you use the microgrid for validation of protection schemes as well?
Well, the answer is, of course, yes. And actually, as a matter of fact, we carry out a lot of testing protection systems. And definitely, having here our microgrid lab has allowed us to do testing of relays prior to going to the field. Recently, we had a project where we have to do the setting of relays for a sugar mill industry. And it was awesome to use here our lab facility to do the implementation of settings into the relay and to test, the settings. So yes, Microgrids Lab, help a lot, to do relay testing prior to going to the field.
Okay, great. Third question we have is, how could the external users access the microgrids for research projects?
Well, we have implemented a cloud architecture, and with the cloud architecture, that we can do is provide an external access to the user, and it depends on the purpose and what will be the reason because they would like to access. But yes, that we can provide some tools in order to access using the cloud architecture. And of course, if the purpose of that is for researching projects or even the training, also we have a support, a technical support engineers that is able to attend any requirement for the external assets. And of course, the laboratory has the open doors if any customer would like to visit us.
Awesome. The fourth question we have is, does NEPLAN licenses, are they requested for the implementation of these controls?
Can you repeat the question, please?
Is the NEPLAN licenses, are they requested for the implementation of these controls?
In this case, that we did was used the NEPLAN web service, and the NEPLAN web service was for calculation only for the power flow solution or the optimal power flow. In this case, we didn't use a licensing, we used the web service. And in that case, it is not requested to acquire a complete licensing. We can acquire software as a service. We can acquire only the calculation, and the calculation could be implemented directly as an engine on the SCADA system. But I think no, it's not mandatory to acquire any license. You can acquire the calculation only.
Okay, awesome. We have two more questions. What is the regulatory and financial impact of smart grids on the utilities sector?
Okay, well, this is quite an interesting question. Thank you. The impacts are many, and we have to handle them in a positive way. You know that at the end of the day, we have to start saying that the microgrids will not pay any money to the utilities. I mean, the idea is to have a balance of zero. So whatever the microgrids require from the system, should be generated by the microgrid. So again, at the end of the year, let's say, the balance should be zero. So a good question is, who is going to pay for the installation that the utilities have on the distribution system? Because still they do have, or they do need to have, lines, transformers, voltage regulators, protection equipment, AMI, etc., etc. If the users are not going to pay any penny at the end of the day, or at the end of the month, or at the end of the year, then someone has to pay for that installation to maintain the infrastructure. So yes, regulatory becomes quite an important issue, and there are many debates about that. I mean, the more users have PV facilities, or the more let's say smart grid facilities appear, microgrids, etc., the less money will go to the utilities. So the impact on the finance and the need for a proper regulation, is important. All I'd say is that all this is very highly beneficial, but of course has to be considered by these regulatory entities around the world, because the issue is worldwide. But yes, that's a very interesting question, and the regulatory issues definitely are being analyzed extensively. Thank you.
Okay, awesome. I'm sorry, we have two more questions. What second to last is, can NEPLAN operate the network by itself?
Well, NEPLAN can operate, it can be integrated in any SCADA system or EMS system, and the calculations can be easily added to the network. However, NEPLAN will send a predictive analysis, and the operation or the primary controls will be done for the controls that are installed on the network directly. But yes, we can implement automation scheme using NEPLAN web services, and the smart solution directly connected to the SCADA system can be the web services. So I think yes, NEPLAN can operate networks by itself, and it depends, because that we can do is a development, and that development is for having an automation and send some reports.
Awesome. And then the last question we have is FERC or NERC compliance needed to implement this application?
Well, in general, our experience in this microgrid implementation is that it requires a big research project only for having a proper management of the energy that we have in our laboratory. And we have had many days and we have found different issues only with the technologies that we have. And I think that if we must, because the IEEE 1547 has the specifications for the compliance or the integration of this kind of sorts, we need to implement this kind of testings, different application or implementation for testing the algorithms and the strategies, cybersecurity, interoperability. All of them must be used. Yes, of course, our microgrid works as a reference point, works as a training. As a trainer, we can use our technologies for giving trainer, but the implementation of each microgrid is for in a specific project, different microgrid, different size of the microgrid.
I would just like to complement what my colleague Leinecker has said, and also indicate that, of course, all the requirements by NERC, have to be fulfilled when we implement the microgrid. So we have to be extremely careful in revising. For example, if we are talking about protections, we have to fully comply with the standards PRC 19, 24, 25, 26, and so on. So even though in some cases the machines are rather small, still, all the regulations that apply from NERC, should apply in this case. Well, I think that with that, I mean, we don't want to take more time from our dear audience here, no?
Yep, that's it. That's all we got for now. Thank you everyone for joining us. As always, check us out on LinkedIn, Facebook, Twitter. Give us a follow. I'll just be up to date with other webinars we got going on in all our projects and just stay up to date. But once again, thank you all for joining us. Thank you, Dr. Juan, and thank you, Leinecker, as well for the informative session today.
Okay, thank you.
Thank you very much for conducting
Have a great weekend, everyone. Take care, stay safe.
Okay, thank you very much also from here.
Bye.
Bye-bye.